Thanks, Debbie. And I really am excited to see all the questions everyone's asking. Right, this week is for you, right? I can do the Rob show all day and not worry about it. But if you're not asking questions and engaged, then really you're wasting your time. So we can run through these slides as fast or as slow as you'd like. Happy to take it from you. I should have made it explicit, but you're being great about this. Ask questions, please. Jump on in and anything you want to talk more about. We can take side routes or go around and backwards, in and out, however you want. We're here to teach you what you need to know, and so keep working with us on that. So as we talked with Phil and Debbie, there's a lot of storage and a lot of bits and pieces going on in here, and absolutely knowing all that stuff is helpful when you need to know how to get the performance. But it would be great if something could wrap all that up and do all the work for you. So we're going to start talking about some more application-oriented data model libraries. And after lunch, Quincy will talk some more about the things that are going on at HDF5. And while we're not quite at the point where we can hide all the details, knowing about burst buffers, for example, is something that's not quite totally wrapped up yet. These will hopefully package up things and over the next few years, roll out more and more optimizations that will make these more complicated computing systems more manageable for you. Everything in computer science is a software stack. We have at the bottom the storage level hardware, the hardware storage actually holding all the data, parallel file systems grouping all that data. There's going to be some kind of transformation going on. And then in this part of the talk, we're going to talk about the data model support, how we take a first step at bridging the gap between the linear stream of bytes that we're all familiar with for files and the more structured I/O needs that applications have. Maybe we live in a three-dimensional world or four-dimensional with time, or if you're a quantum physicist, 16 space-time dimensions. I don't know. Point is, our data structures are more complicated than just that which is provided by storage, and these libraries are where that begins. It's not perfect yet. We're really good at handling multidimensional arrays. We're less good at general I/O libraries for trees and meshes, although there are some that are okay on that part. Fortunately, there's lots of multidimensional array problems, or ones that can be squished into multidimensional array problems, and so we'll talk about that. The nice thing about these libraries is that they provide not only a higher level interface and a collection of routines to help manage data, but they're also dealing with the layout of data on disk. I was talking at the break with someone from NASA about some legacy data that was created on a big Indian platform, and now he's got to look at it with a little Indian machine, and now he's got to worry about byte swapping, and it's not impossible. He'll figure it out, but it would be great if it would just do things for you automatically, and these libraries do just that. And maybe it's the implementations might be a little bit different. Maybe one library like Parallel-NetCDF will always be big endian. I will always byte swap the data and always write it out in big endian. HDF5 will defer that operation and maybe only pay the cost when you have to. But in any case, the user doesn't really worry about that. The library provides that portability. And then again, it's not so much about the data itself, but having more provenance and some more annotations on the data can help a whole lot. If you need to know where this data set came from and how it was produced, or who do I bug to figure out more about this data, or even if you're telling yourself 5 years later why you generated this 4 terabytes of data, these actual annotations and descriptions can help understand that. And those annotations can help do things like indexing and other additional features. We're going to come back to the game of life example, but take a side detour here and spend a little bit of time on Parallel-NetCDF, a library we work on at Argonne in collaboration with our collaborators at Northwestern. And I suppose I should really say Northwestern does all the work these days. I'm sort of just the spokesperson for it now. I commit much less code to it than I used to, but I'm still a big fan of this library. It's simple, but it gets the job done in a lot of cases. And even though we host a mailing list, we'll make sure Northwestern gets the credit that they're due because they do a lot of work on this library. So the story of Parallel-NetCDF is that in the early 2000s, we're looking at I/O libraries that are being used by applications. And we have a lot of people at Argonne who work in the climate codes, and they're telling us, like, we've got this very widely used library, but the performance isn't what we need. We need a parallel way to do this data now. Back in the old days of 2000, there was a big transition from the classic Cray machines to parallel processing, and so they have to worry about, they spent all this time on parallelizing their computation, and they were just getting to look at their I/O side. So we look at Parallel-Net. We can take the serial NetCDF interface. This is a very old library produced by the folks at UCAR. And then we can keep that file format, keep all of the semantics and rules of that file format, and then provide a different interface for it. And so that's the Parallel-NetCDF interface. It's a little bit confusing because in the subsequent years, there's now a Parallel-NetCDF interface, but a long pause between those two things, done by Unidata. So now we have classic NetCDF. We have Parallel-NetCDF from Northwestern and Argonne. We have Parallel Unidata NetCDF, and then we have HDFI. So it can be a little bit of a mess, but we're all collaborating and working on the same I/O problem. So it's more of a naming muddle than it is anything else. Just something to keep in mind when you're looking at the different NetCDF solutions that are out there. There are a lot of, again, there's some commonalities between those different versions of NetCDF. Parallel-NetCDF, like Unidata's NetCDF, describes, here's a big file called a NetCDF data set, and that file will contain a collection of variables. And then those variables will have multidimensional arrays of some kind of type, of integers or floating points. You'll be able to annotate those variables or the data set itself with information. And we'll see plenty of examples of that. There's a variety of different bits and pieces that go under the hood here. The thing that helped a lot of climate people adopt Parallel-NetCDF quickly is that while we're providing a new interface, which makes it very explicit this is a parallel interface, and it's not a drop-in replacement. We can just drop the libraries in and get things working. Because it makes some source code changes and call these parallel NetCDF routines. But the generated files are perfectly compatible between Argonne and Northwestern's version and Unidata's version. In fact, Unidata has a spec, and we followed the spec very closely, and we found a couple cases where we were a more NetCDF-y file than they were. They were a little bit, so for example, anyway, we just followed the rules very carefully, and they were not following the rules as carefully as we were, and we found a problem. Hey, you should be more compliant with your own standard. And of course, they were happy to fix the problem. It was just one of those things. Whenever you have anybody else follow your own standard, you realize where the gaps are. I'm sure Quincy can talk more about that too. You've seen this before. Phil talked about how you think in a climate term about a chunk of atmosphere or barometric pressure across a patch of the land. But in the end, it becomes much more computery under the hood, right? There's a description of what kind of type it is and the size of the space, and then importantly, the units, right? The file system doesn't know what units of data are. That's extra information you provide. That's semantic information you can provide to the storage device. And you can have different numbers of dimensions and different units, and then here, this tucked away, hidden from the user, is the offset in file where this variable starts. And then you have in NetCDF very regular chunks of data. The first variable is all here, and the second variable is all after that. We can do this. I'll show you a little bit more why we can do this. Because we're pre-declaring all the data, but it lets things be really efficient for reading and writing. There is one catch, which when we implemented this library back in the early 2000s, said, well, we'll just tell people don't do this. Record variables are a little harder to implement because these are variables that grow over time. You could imagine a sensor in a field collecting information and then appending a new temperature or wind speed value to this variable in a data set. And if you only have one record variable in your data set, there's not much of a problem here. But when you have several record variables, they are interleaved. Picture a deck of cards, and they're all going to, the first record of each variable will occur, and the second record will occur. And so if you are doing if you're trying to read all the data from one record variable, you're going to be walking through the file in a very non-contiguous pattern. And much to our chagrin, record variables are used all the time in climate codes. We were hoping that wasn't the case, but there's some tuning you can do to get this better, but that's an aspect of Parallel-NetCDF that doesn't perform quite as well as we would like. So that's something to bear in mind. It's pretty odd. I don't see this kind of approach taken very often in IO libraries, although if you squint and look back a little bit, it is a little more common. This idea of a bimodal interface. In NetCDF, and by extension Parallel-NetCDF, you have a define mode where when you write a data set out for the first time, you are declaring all of the values you want to store up front. I'm going to have, my data set will have the following variables. Each variable will have the following shape and type and size. And now I'm done declaring all my variables. I'm going to switch into data mode. And now I'm going to write those variables. And this is a bit of a headache because you have to think ahead of time what you're going to do. But if you're willing to pay that upfront cost, then the storage behind the scenes can not worry about free block allocation or discontiguous data. It can just make sure everything is exactly where it needs to be as it's used. So, right? If you know you're working with a three-dimensional variable, you can algorithmically compute the offset for the X, Y, and Z parts of that. And so now everything is pretty efficient, especially in the case of parallel I/O. This decoupling of intent from execution is used in a couple places in the I/O stack. If you think about non-blocking communication in MPI, you post a bunch of non-blocking sends, and you're telling the library, I need to send this information. It looks like this, and I don't care about it yet. And then you keep posting, and then you wait for completion, or you test for completion. And that test or that wait is when you're telling the library, hey, I need that information now. Please get to work on it. And under the hood, the library will stitch together the request, or do something efficient with it, or do something fun to make more things go at the same time. Similar idea here. You tell the library, I want to do this, and now I'm going to actually do it. In a couple slides, I have an example of how write combining several Parallel-NetCDF operations with what looked like a non-blocking interface. It generated a big performance gain for a Flash workload. Same deal. I'm going to tell the library about these operations, and now I'm going to do them. And we've used this a couple times in different approaches, in different libraries. And so what's going on inside define mode? Well, you saw all the nuts and bolts of what goes on in MPI/IO in our game of life example earlier today. Define mode can do some of that stuff ahead of time. It can create the file if it doesn't exist already. It can perhaps do some tuning to the file system if it knows something about the structure of the file. Maybe it can line up some variables based on file system block alignment, if that makes sense. And then, because everybody is declaring the same header information, rank 0 can cache that information, and then doesn't need to worry about exchanging any information after define mode exits. And once you end define mode and go into data mode, we can do a small header write, and then continue on without any other communication between processes. So that part is really attractive from a parallel I/O standpoint, because once everybody knows what's going on, the different ranks can all do their I/O, and they can know what everybody else is doing, and not worry about invalidating anybody's block or anything else. And we'll see in some of the code examples, there's in Parallel-NetCDF, we, like MPI/IO, explicitly indicate which routines are collective with an _all suffix. Those collective routines, in this case, NCMPI put vera all, are saying, I'm going to take this variable, which I described earlier, and I'm going to place it into the data set collectively. Var A means a subarray, so that's a natural way to decompose a n-dimensional array across multiple processes. And then under the hood of that, you'll see there'll be a file set view, and data types are created on the fly and then written out collectively. This is an older tool called Jump Shot, and I really adore this tool, even though it's not supported anymore. I still find myself using it from time to time because it's a great way to trace what's going on at the MPI level. I haven't, in this case, in this example, I haven't done anything to capture Parallel-NetCDF calls, but because there's not much gap between what Parallel-NetCDF is doing and what MPI is doing, it's you can sort of project forward and see the different MPI Parallel-NetCDF calls through this MPI call trace. On the y-axis here is processes, MPI processes, and the x-axis is time. So when rank 0 does an independent file write of the header in Parallel-NetCDF, that shows up as an itty-bitty gray sliver here from rank 0. There's a little bit of opening, a collective open happens over here, and in this faint pink area over here is the close. In between is the write of some information. I guess I'm a little bit out of order here. The Flash Astrophysics code is going to write out adaptive mesh structures. Now, Parallel-NetCDF is not an adaptive mesh library, so they do some things to make it, the Flash people take their adaptive mesh structures and then they store them as Parallel-NetCDF variables. There's a step here where there's a few small variables written where they write out the grid and the leaf node information. And then there's going to be 4 variables of interest written out to the file. In this case, we're tracking collective writes. There's no coordination here. There's no all gather to see who wrote where. There's no point-to-point coordination. All the processes know where everybody's writing. So when they write out variable 1, variable 2, variable 3, variable 4, they know where to go without where each variable is going to live in the file. There's no coordination or anything has to happen there. This is a collective operation. You'll see that some of these processes take a much longer time than others. These are the I/O aggregators. Sorry, these are the MPI I/O aggregators. Those are the processes that the MPI library picked to actually write the data out. We don't know anything about this at the Parallel-NetCDF layer. We're just saying to the MPI library, go ahead and write this file out the best way you know. And the MPI library picked one process on one of every 4 processes to be the I/O aggregator. And those are the ones that actually do I/O. See, I like this example because I've seen this happen at least 2 times off the top of my head, probably more often than I know. Process applications will say, okay, I have 1 million CPU nodes and I know I'm going to hammer the file system. I'll just do I/O for my first 10 processes. That's a good instinct. But if you pick the first 10 processes on this machine I think this was, if it's 4 processes per node, it must be our Intrepid machine. But in case, it doesn't matter what it is. In this case, if you pick the first 10 processes to be your I/O nodes, you would be funneling through only one BlueGene I/O forwarder. You'd be all jammed up on one set of cores on one compute node, and you would observe very bad I/O performance. And then you would throw your hands up and say, well, this machine's terrible. I hate computers. However, if you let the MPI I/O library do this for you, then you're going to save yourself a lot of headache. The I/O library will take care of placing the I/O workers where it makes sense. The MPI I/O library on BlueGene knows how to query the topology and place the aggregators such that they're all going to different I/O nodes, and you'll get the best throughput. Often BlueGene was a nice machine in that regard. Sometimes I/O tuning was a simple matter of just saying, well, why don't you just do collective I/O and let the library do all that work for you? And a lot of times that was all you needed. That's a lot of time on one slide, but this is a pretty dense slide. A lot's going on here. And this is a simple MCMPI put Vera all call. One routine is causing a lot of magic under the hood, so I'll just take a little bit of time here to go into that. The write combining optimization is fun because you're able, again, this is the same theme. it looks like a non-blocking operation. And we might think that non-blocking means, well, I'll post this operation and then in the background I/O will happen for me. And that might be the case in some libraries. In this case, this looks a lot like MPI non-blocking communication. We describe what we're going to do, and then there's a request object that we can then wait on later. And so again, we're describing all the data up front. We describe the purple section here. It's going to be four values here and 4 values over there. And then in the green call, the green is it's a wait all, it's a collective wait. Well, then all those requests will get put together into one efficient blast out to storage. Now, or maybe not, right? Maybe we have burst buffers. Maybe we'll do variable by variable I/O. The point is the library can make that decision for you, maybe with a hint or help from you, and all you've done is give it more information, and then it can choose either way. It can choose a low latency, high IOP approach, or it can choose a high bandwidth approach, depending on what the right thing is there on the topology. Machines are going to get more complicated if we can help the libraries with more descriptions of our work and more robust interfaces, then we'll have a better chance of getting the performance we want to see out of these machines. So back to game of life. We saw how we did the MPI I/O version, and so now you've got a concrete example in your head. You've seen sort of the hard way to do it, and now we'll do it a much easier way. You know what happens behind the scenes, and we'll walk through this a little bit. There are the same constraints and concerns as before. We want to collect this checkpoint information in a single file. We want to have a canonical representation, which means we're going to ignore our ghost cells or any extra information. We only want the relevant information stored in the file. And we can add as an attribute the iteration of this checkpoint. So if we're running 20 checkpoints, we want to step back in time and restore the 10th checkpoint. We can look at the attributes and figure out which one that is, and then get that data loaded. And if you tell somebody, hey, I've got some data in a NetCDF file, they'll be able to query it and look at it and not know anything about it ahead of time. I'll show you some examples of how those those query interfaces look in a few slides. More code. It's all living in that same Git repository we talked about earlier. It looks a lot like the other examples, the standard I/O and the MPI I/O one, because right, we're hiding all the details below this interface. Not much to talk about here. Duplicating works. And then here's some actual Parallel-NetCDF calls. It's a collective call. Looks like an MPI I/O collective call. We describe the communicator we're using and the modes. So, and then as soon as you, and the other point I want to make is, as soon as you create the file, you're in this define mode. So you won't see any code to put you in this bimodal describing interface. You end up there right away when you create the file. So if we're going to describe how we're going to write out to a file in a Parallel-NetCDF file, we have two things to worry about: describing the memory and then describing where we want it to go in the file. So to walk in a little more detail, the put vera all call takes an NCID identifier, which data set are you writing to? The variable identifier is which variable that of the many variables you've described, which one are you talking about? Then a start and a count is all you need to describe which part of the n-dimensional array you're working with. If you're working with the entire array, then the start would be 0, 0, 0. If say it was a 3-dimensional array and you're writing the whole array, the start would be 0, 0, 0, and the count would be all the dimensions. But of course, we're decomposing across multiple rows, so we're going to do some math to figure out which sets of rows we're working with among all the processes, and write that out. That's the file side of things. The memory side of things looks a little different. You have the classic buffer count data type tuple that's used in all kinds of MPI message exchanges. And so in this case, it's just a blue blob, but you could imagine a more complicated data type describing points in a simulation or a more complicated structure. Because we are using MPI data types to describe what the users are doing, our interfaces are a lot more straightforward. Sorry, not more straightforward, more flexible. A little bit of a trade-off here. There is a put vera all int, which would say this buffer I'm giving you is going to be integers or floating point numbers. And then the NetCDF will take care of doing whatever transformations are required, right? You could imagine a buffer full of double precision, high precision information in memory, and because you want to write out very quickly, and your algorithms are resilient to a little bit of precision loss, maybe you're going to store it in single precision floating point numbers. The library will take care of that for you. It'll truncate, it'll cast all of the double precision floating point numbers to single precision floating point numbers, and then write them out at half the size. So 2 things to point out in this code sample. We have a section up top where we are doing the descriptions. We are just talking about the variables, and so first we define the dimensions. We have a row and column dimension. It's going to be however big the problem size is, and then we associate those dimensions with the variable. Now we know that this variable matrix is row by column. Then we swap out of define mode, and then we start talking about where we're going to write into the file. And again, just as we showed earlier, that could be 0 rows, it could be many rows, it can be irregular. That's same problem, same thing here. You can have as little. Your data decomposition can be disorderly or orderly or anything in between. So checkpoint is pretty simple, right? We have described the data, we have described the memory a little bit. We have this type create row block that we saw earlier is describing the user's memory, and then we dump it all out to the file with this put var all call, and it all happens. All that stuff you saw in that timeline chart goes out to the file. So pretty concise. We've hid some things in functions, but it all maps to sort of a logical understanding. We want to describe this data, describe the data in memory, describe the location in the file, and then go. There's no coordination here. Rank 0 should be something like this, or rank. It's just we're all going to write out our data. Reading is a little bit. It's not too much different. We open the file instead of create it. As I mentioned, there's a parallel version of the NetCDF interface, and it seems like they've compared notes here a little bit. The same things that we added to our interface to make it parallel are available in the open par interface in Unidata's NetCDF. The idea of a communicator, the idea of an info structure, but other things are the same: the file name and an access mode, and then getting back a NetCDF identifier. We're checking our error messages because we're good citizens, and then there's a little bit of inquiry. So let me step back a little bit and talk about a self-describing file format. The library gives you the tools you need to query the file and interrogate it and figure out what's going on. So once you know a dimension, in this case, you've got an array of dimensions, and you want to figure out how big is the 0th dimension in this file. You can inquire the length of the dimension, and you'll get back in column dim size a value. And you can go through and read this file, and so you can write a general purpose restart reader that can be flexible no matter how a checkpoint was generated and do the right thing. This is more error checking than actual code, which is great. The idea here is that we have looked at the attribute on the file, and then we know, which variable are we dealing with. If we don't have a variable here, then there's a problem. We want to get which dimensions are associated with this variable. Then we inquire on the dimensions, both the column and row sizes. I'll show a couple more examples of this part because I think it's worth understanding how we get information out of the files, not just producing the files. Again, there's a little bit of error checking going on here, making sure that everyone's has enough memory and no one's bailed out on us. And then we can go here and do a collective read of the file, and then go through and assign this buffer. The buff that we read from the file can then get assigned into the matrix. I think if we were a little more clever, we could probably skip this assignment step, but that would require a little bit of some tricky MPI data types. Sometimes it's just faster to do the assignment. Memory's pretty fast relative to storage anyway, so there we go. So things you don't need to worry about when you're using a high-level I/O library are things like setting up your own types or attributes. That all comes along for free. We're able to describe how that data is laid out in storage, so that we can, how the conventions may be different, but you can query the file and figure out what is in this container and figure out what's going on. And there's all kinds of optimizations that are happening under the hood that we don't need to worry so much about until you're the advanced levels of really trying to get that last bit of performance out. But often, some of these first steps get you most of the way there. I'm going to talk a little bit about some applications that are using Parallel-NetCDF and how they use it, so we can. It's not just a toy research library. This is actual applications that are using these things. And sometimes it's a natural fit. Sometimes, especially in climate code, there's the idea of a latitude, longitude, and altitude, and that fits very naturally to Parallel-NetCDF. But as I mentioned with the timeline chart, Flash's data structures aren't quite like that. Flash is using adaptive mesh refinement techniques so that it can scale its supernova simulations to very large supercomputers. And of course, this part of the detonation is very boring, so there's going to be a very coarse grain, but this part of the detonation is very exciting, so we're going to have a very fine grain mesh there, and capturing all that information for the subsequent restart or visualization is pretty important. Just like our game of life example, we have ghost cells that we're keeping around for communication. This is and optimization, but they're not important to the simulation's checkpoint information. When we restart, we can make those copies and do that, but it's not important to save for storage, for persistent, for either the checkpoints or the movies. Neither one of those cares about the ghost cells. So when we write out this checkpoint, we're going to ignore that. And Flash runs everywhere. They've run on it. They're one of the first codes running on any supercomputer, and so they're very, very concerned about portability and making sure that they have sort of the Flash file format that they can then take either back to their lab to study or take to a different visualization cluster to study. And so these are all factors that make it a good use for a high-level I/O library. And so they did all the right things. They're very good I/O citizens. And they still weren't quite getting the performance they wanted out of Blue Gene. So they came over to Argonne. We're only half an hour away down the road from them, so we talked to them a lot. And we were trying to think about what can we do here to get better performance. Well, they had two different choices here. They could have changed their file format, and instead of writing one variable at a time, they could have described a more complicated I/O pattern and written all to one single variable. And that got a good jump in performance. But it broke the file format for all their visualization and other consumers of this data set. Now they're on version, at the time they were on version 10, so clearly they've changed the file format in the past. It's not impossible. But they would like to not have that overhead if they could avoid it. If they could just get good performance without changing the file format, so much the better. Well, that right combining optimization I mentioned, where we could describe the pressure and the temperature and the velocity variables, was what they applied that here, and we're able to greatly improve performance here. That's because each collective I/O has some coordination going on. So the more data you can stuff into that call, the more you can amortize that communication and synchronization cost. I should say the synchronization cost is probably more important. The communication part on modern systems is negligible. But as you enter a collective call, processes that are lagging behind, maybe because they have more data or they are computing a more interesting part of the simulation. Until they enter that collective call, nobody can make progress. So sometimes you'll see collective calls look slow. Like you put a time between each start, end, and you'll see a lot of time spent in the collective call. Sometimes that time was waiting for everybody to catch up. That's harder to quantify. So sometimes your first impression may be that collective I/O is slow, but really it's more of an imbalance thing. And there's some things we can do to fix that with non-blocking collectives. But another way to fix it is use this non-blocking interface, combine everything into one single call, and then issue all the I/O at one time. Another heavy I/O user are the cosmology folks. The HACC cosmology code is modeling the universe, which is you can do that on a supercomputer these days. There's something like 13 billion years of universe time, right? And so you look at the sky, you take a detailed sky survey, and you say, okay, well, here's how things look now. Let's run back the clock and simulate the Big Bang to now. And if our simulation looks kind of like what we see in the sky, then we must have a good understanding of the physics, of the scales that are going on here, of the way that these gases and particles interact. And if we do the 13 billion year simulation and what we see it bears no resemblance to what's in our simulation, then we have to rethink our physics and our models. And of course, this is one of those examples where the more particles you have, the more computation you can apply to it, the better your simulation is. The first cosmology simulations were 200 particles, which sort of blows my mind that would be enough to do any science with at all. But as a friend pointed out to me, the telescopes we had back then were very meager too, so we didn't have very detailed structures of the universe. So it was sort of a blobby simulation of a blobby visualization, and we sort of, okay, it's fine. But now with 13 billion years and 2 trillion particles, we're getting a lot better understanding and confirming our physics and our physics understanding, right? Because none of us can go back to the Big Bang and see what's happening with the scale and calipers, right? We've got to do this all in with math and simulation. The HACC guys they collaborate with everybody, they try everything out, and some things don't make it into production, but one of the research areas we tried was, can we use Parallel-NetCDF to hold 13 billion particles? That required a little bit of a change, but there were a lot of things that were good about it too. Parallel-NetCDF provides the metadata, and here's your experiment size and when you ran it and some information about it. As we saw, there are all these particles, and they all have different mathy, physical things that they're interacting with each other. But where they are, so we have the notion of a billion particles, but the particles, I should say, the data structure holding the particles doesn't move around. We just update their x, y, and z position. So we keep a data table of all the different particles and what they're doing, what their properties are. And so now, if you look at the index, you can say, okay, well, I want to know all the particles that live in this space, and the index gives you the following particles live in that space, and now we can use some different routines to figure out what's going on there. So how does it look in practice? Well, HACC is one of the few C++ codes. I guess there's probably more C++ codes going on nowadays, but at the time it was one of the first groups to sort of, okay, we're going to throw away all this old code and redo everything with modern C++. So in the constructor, they're creating the data sets. They're using this new 64-bit data flag because we have so many particles that we needed to extend the NetCDF file format just a little bit so that we could describe very, very large variables. And you can see here, when they write the metadata out, they're passing a lot of information here, but they're going to store a global attribute describing what's going on, what's interesting in this data set. If you have something about minimum z values, you saw that globally too. When it comes time to define dimensions, again, you put attributes on that variable. Here's an example where we're defining attributes on not just the data set itself, but specific variables, defining units and variables, and then we put the attribute into the file. Finally, when it comes time to write data, there's this is the classic example of a process that is writing an irregular amount of data from every process. Sorry, a program that's writing irregular amount of data from every process. So we use MPI XScan to figure out who has what particles where. At this point, in a particle table where you live, and we can reduce the total number of particles. Everybody, all 100,000 processes say how many particles they have and where they are. And now, after you call XScan, it's an exclusive scan operation. Everybody gets, in the end, so rank 0 gets the first value, rank 1 gets its value plus rank 0's value, rank 2, so on and so forth. So the millionth process knows, okay, there were 2 trillion particles, so I'm 2 trillion and 1. The 1,000th process knows where it fits in, and everybody can then use that value for their start and count calculations. And now they do a collective write of floating point information, and here we go. On the Parallel-NetCDF website, you can find a quick tutorial. I've referenced that in our Git repository, I hope, which shows you some examples of how you would both write and read data and use the read inquiry routines to figure out what's going on. But I can also cut out a lot of the error checking and other stuff and fit it all on one slide. So if you don't know anything about the file, first principles kind of coming into a file, you need to figure out what is in the file, how many variables, dimensions, attributes are in this file, and then for each one of those dimensions and variables, well, how big are they and how are they associated? I guess so step one is what's in the file, 2, how big are the dimensions, and 3, how are they associated with variables? If you are a climate code and you know you're always going to read climate code, they have these things called, they call them conventions, that's the terminology. And you know you're in convention 4, you might skip some of these steps. You know every data set you get is going to have 6 variables and 3 dimensions, and you can just go right to the file. And any deviation from that is an error, and you can throw an exception and say this is a corrupted file. So, but if you don't have that luxury, then you can still make progress and figure out what's in the file. So there's first a general inquiry, and inquiry, you pass it a data set, and it tells you in return how many dimensions, how many variables, how many attributes, and this idea of are there any unlimited or record variables in the file. You have to do something, you have to treat your record variables a little bit differently because they have an unlimited dimension, but that's not the case in this simple example. Then finally you can go through, so next you go through and you know you have 10 dimensions. So you go through and you can inquire each dimension and you put it in this array of dimension sizes. And then because we know that Parallel-NetCDF and Parallel-NetCDF counts everything from 0, we go through here and inquire on the variable, what is your name and type and how many dimensions do you have and what are the identifiers associated with that. So you'll go through and okay, the third variable has dimension 4, 5, and 6, and we know from our array that that's 1,000 by 512 by 4. And we can look at the types and everything, and then now we know everything about that variable. So to wrap things up, there are more complicated I/O libraries out there, more sophisticated, I should say, I/O libraries. But if you're just working with multidimensional arrays of type data, and you don't need a lot of flexibility in your data descriptions, Parallel-NetCDF Parallel-NetCDF would probably be a good fit. There's very little overhead in using it. In fact, in some cases, we can provide some optimizations that make it faster than writing an MPI/IO version directly. If you're using the very common but older CDF2 format, you have to have small variables. We changed that in this thing called CDF5, and because we are trying to be good citizens, it took a while for us to push that upstream to the serial NetCDF folks, the Unidata folks, I should say. But now there is this CDF5 format. This big variable format is you can check out NetCDF and you can now once again the biggest files you create in Parallel-NetCDF can be read by Unidata's NetCDF and everything's happy again. So anything I can talk to you in particular about Parallel-NetCDF or how these applications use Parallel-NetCDF or how you might use Parallel-NetCDF? All right, no problem there. I have a few hands-on examples in the Git repository, but I'm always around to talk about this stuff. And when Quincy talks about HDF5, you can compare where HDF5's strengths and weaknesses are to HDF5 to Parallel-NetCDF. It's a good the two libraries make a good point of comparison as far as giving users lots of options or giving users very few options. I think Parallel-NetCDF represents a sort of a tightly constrained I/O library, and that has some weaknesses, but also some strengths. And HDF5 has very much a very powerful library that has some verbosity along with that too, and some overhead. So it's good to compare the two. I think they make a good. I'm glad Quincy can come out and talk about his library as well.